Hello students, today I am going to discuss how to solve problem by using Mollier chart. I am taking one problem. Problem is like this. A steam power plant operates on a theoretical reheat cycle. Steam at boiler at 150 bar, 550 degrees centigrade expand through the high pressure turbine. It is reheated at a constant pressure of 40 bar to 550 degrees centigrade and expand through the low pressure turbine to a condenser at 0.1 bar. Draw the HS diagram. Find the quality of the steam at turbine exhaust. Second one is the cycle efficiency. Third one is the steam rate in the kg per kilowatt hour. See how to solve this problem. First, you take given things. Write the inlet step condition in the high pressure turbine, that is a 150 bar, 550 degrees centigrade. Reheating pressure 40 bar and reheated pressure is given 40 bar to degree centigrade. Condenser pressure is given 0.1 bar. Step 2, what are the finding parameter? Quality of the steam at turbine exhaust. Second is cycle efficiency, steam rate in kg per kilowatt hour. See, once you read this problem, you can get this is the simple Rankine cycle with the reheating method. And next step is check the inlet condition of the turbine. How to check inlet condition of the turbine? Refer saturation pressure table at 150 bar. What is the saturation temperature? 342.1 degrees centigrade. See now this whatever 342.1 degrees centigrade, this temperature is less than inlet temperature. See, inlet temperature is given 550 degrees centigrade. It is less than 5. Now given condition is superheated condition. See, you can refer steam table. See 150 bar. This is a steam table. These are the pressure, saturated pressure table. At 150 bar, see saturation temperature is 342.1 degrees centigrade. So now given temperature is 550. That is a 550 temperature is more than, that is a given saturation temperature. Hence superheated, this is a inlet turbine condition is such superheated condition. See, once you know this one here, all the inlet condition of turbine, next step is to draw the HS diagram by using above the data, that is a HS diagram. H correspond to enthalpy, S correspond to entropy. Basically in the HS diagram we have a three pressure. One is a boiler pressure, that is a 150 bar. Another is reheating pressure 40 bar. Last one is condenser pressure is 0.1 bar. See, already we got this one inlet turbine condition 0.1, that is a superheated condition. Now you need to look at the first point, that is a superheated condition. Expand, that is a in the high pressure turbine up to reheating pressure. That is a 0.2 you are getting here. Again at constant reheating pressure, reheated at 0.3, temperature 550 degrees centigrade, and 3 to 4 is in the low pressure expansion process, it will be reach the 0.4, and 4 to 5 is, there is a heat rejection process, and 5 to 6 is pumping process, 6 to 1 is heat addition process. And we just observe from the HS diagram, we have two types of heat addition. 6 to 1 heat addition will be calling as a heat addition 1 in the boiler, and again one more heat addition we can find here from 2 to 3, that is in the reheating temperature. Once you draw this one HS diagram, go to the refer finding all the enthalpies from the HS diagram. We can able to get enthalpies H1, H2, S3, H4 from the Mollier chart, H5 by using stream table, and H6 by using a general property equation. We can find this one here, H6. Let me start to calculate all the enthalpies. We know this one here, temperature and pressure. See, just to refer this enthalpy, 150 bar, along this 150 bar, it will be cuts with what here, join with the 550 degrees centigrade. H1 we can get it. From the 1 to 2, this is what isentropic process. From the high pressure turbine, it will be joined with reheating pressure. You can get the H2 here. And again at constant pressure, heat will be adding at constant pressure. It will be joined with 550 degrees centigrade according to given condition. And 0.3 your enthalpy, we can get the values from the chart. From 0.3 to 4, again we have a isentropic expansion process in the low pressure turbine, and it will be joined with a condenser pressure. See, this pressure is, this is a 0.1 bar, join with, this is a straight line, it will be, this pressure is constant, both will be joined in the single point. That's what we'll be calling as a H4 we are getting. See, at 0.4 we can calculate this dryness fraction. See this one line, you can get the X4, this is a dryness fraction in between these two values. See, once you have located this all the points H1, H2, S3, H4 as well as dryness fraction. See, find out corresponding values by referring the this one values. Okay, values given in the what here in the y-axis enthalpy. H1 you can get it, H2, S3, H4. See, I am going to write this all enthalpies. H1 is equal to, we got 3450 kilojoule per kg. H2 we can got 3055 kilojoule per kg. S3 is equal to 3560 kilojoule per kg. H4 is equal to 2300 kilojoule per kg. And along with this dryness fraction at the turbine exhaust, X4 is equal to 0.8. These all values we are getting from the Mollier chart. Again, how to find this H5? See, H5, we know this particular H5, already I have told this is H5 is now dryness fraction is 0. It is a purely is a liquid form. That's what H5 is equal to HF. See, operating pressure is, condenser pressure is 0.1 bar. Refer steam table. See, now you can refer the steam table at 0.1 bar. See, we have this HF, HFG, HG. See, H5 belongs to what here, liquid. That's what we need to refer. That is a HF only. That's a H5 is equal to how much value? 191.8 kilojoule per kg. Similarly, I'll be find that is a H6. We know this pump work is equal to H6 minus H5 as per this one here formula. And again we applying pump work is equal to, by using a general property equation, VFI, boiler pressure minus condenser pressure multiplied by 100. See, now why we are going to multiply by 100 here? See, boiler pressure as well as condenser pressure, these in the bar we are going to convert into kilopascal. See, whatever value we have to convert into kilojoule per kg. And again this particular VFI we are going to find out from the steam table. Operating pressure is again 0.1 bar. Refer saturated pressure table. You just write it here, 0.001010. And the boiler pressure is, as per given the value, 150 bar minus condenser pressure is 0.1 bar multiplied by 100. and H6 is unknown, and H5 we have found from the steam table 191.8. And after this calculation we can get the H6 is equal to 206.93 kilojoule per. You observe the values of H1, see lesser the value and slight increase in the H6. Okay, now we are going to consider the pump work. See, next step is we are going to calculate the Rankine efficiency. Rankine efficiency is equal to, as the equation, net work divided by heat supply. See, net work we can write in the turbine work minus pump work divided by heat supply. See, observe this one here. Turbine work is equal to is the addition of both expansion process in the high pressure turbine as well as low pressure turbine. That's what I am going to write is a WHPT plus WLPT minus pump work. Again, you know this one here, heat addition taking place in the what here in the boiler as well as reheater. I am going to write the QS1 plus QS2, and you just refer this HS diagram. See how to write this one here. Work from the high pressure turbine H1 minus S2. Similarly, work from the low pressure turbine S3 minus H4. And pump work we can write this H6 minus H5. And heat addition we can write this, always you need to take a higher minus lower, H1 minus H6 in the boiler. In the reheater we can get the heat from the H3 minus S2. See, once you know this one how to write the enthalpies, okay, you substitute all the enthalpies what you have calculated in the Mollier chart. See, just we have elaborated work in terms of enthalpies. WHPT is equal to H1 minus S2 plus WLPT is equal to S3 minus H4 minus WP H6 minus H5, and heat addition in the both first stage and second stage, H1 minus H6 in the boiler plus S3 minus S2 in the reheater, and substitute values and H1, S2, S3, H4, H6 here, and calculate this efficiency 43.75%. Similarly, we are going to find out that is a steam rate. See, steam rate is equal to, we have formula 3600 divided by net work. 3600 divided by net work is nothing but difference of turbine work minus pump work. And again, this 3600 divided by turbine work is a expansion is happening in the two expansion process. One is in high pressure turbine, another is a low pressure turbine, and minus pump work. Already I have discussed how to write the enthalpy. And WHPT we can write H1 minus S2 plus WLPT we can write S3 minus H4 minus pump work H6 minus H5. See, substituting all the values as given in the previous slide, and you substitute and get the value is 2.19 kg per kilowatt hour. In this way we can get how to use the Mollier chart, okay, and how to find the enthalpy. Thank you.